What's good, everyone? In today's video, we'll be continuing on with the Hugging Face series. And today I know I have quite a large title there. Don't get overwhelmed, we'll explain each and every component of that very simply soon. But what I wanted to explore was fine-tuning Llama 3. We'll take their 8B bottle today. And we'll explore PEFT, so parameter efficient fine-tuning. This is a technique we've talked about in the past, but I'll quickly overview what PEFT/QLoRA is if you're new to what that is. I'll also link down below the research paper around QLoRA and PEFT, which I highly recommend reading. You don't need to understand all the math. I'm not a data scientist either. I don't understand all the linear algebra nuances fully, but you'll get a general understanding in terms of what's being implemented there. And along with that, right, speaking of implementation, we'll talk about where does Hugging Face exactly help in terms of simplifying this process and how we can conduct supervised fine-tuning that will basically implement PEFT for us here using some of the constructs within this. So as I said, kind of for the agenda, first we'll theoretically overview at a higher level what PEFT/QLoRA is. Like I said, if you're more into the math or data science side of things, I'm definitely not an expert there. I would read through the paper there, but at a high level, I'll introduce what exactly is happening here. And then we'll talk about HuggingFace's Transformers Reinforcement Learning Library. That was a mouthful right there, but the TRL library right there, we'll talk about it, and how you can specifically use certain kind of offerings it has, such as the SFT Trainer, to implement PEFT and QLoRA in a pretty kind of simple manner or way. And then we'll get hands-on, and like I said, we'll do a Llama 3 example here, Llama 3 8B, but you can apply this, right, after you get a general understanding to kind of whatever model you're comfortable with, depending on your use case. So with that being said, let's get right into it. So for PEFT and QLoRA, it's kind of in the name itself, parameter efficient fine-tuning, and QLoRA is quantized LoRa. It's a form of parameter efficient fine-tuning. But with PEFT, right, the reason this is needed, right, with LLMs is, as we know, they have billions of parameters, and it's only scaling in sizes as these models get more and more complicated. With full-scale training, right, you're going to have to update all the parameters whenever you want to customize this or scale this up, basically. And that's not really feasible, right, to do every single time, especially if you're on a bit of a budget restraint or time restraint. Updating all the parameters is very compute and as a result, cost intensive, right? To do full scale training. And there are options like that. We've talked about things like SageMaker Hypercloud before, where you can do kind of cluster based training where you have multiple different nodes that you can manage. But in most cases, you don't really need to do full scale training. And it's also just not feasible due to the pure amount of compute that's required to update each and every single one of these parameters. So that's where PEFT got introduced, where people were essentially looking for techniques where you can maximize performance and get similar benefits, right, to full scale training, but similar, maybe not the exact level, maximize performance, but only update a subset of parameters. So can we take selectively from the model just certain parts of it, right, essentially, and update and train them, but not necessarily have to go through the process of training every parameter within the model, right? And this would save us a lot of time and compute resources as well. And from this concept evolved something known as QLoRA, which is the most popular PEFT technique, at least that I'm aware of in the industry. I might once again not be completely aware of like the latest kind of data science kind of breakthroughs here, but QLoRA at least is pretty widely adapted, and it introduces the concept of adapter weights. So what happens is, right, if you have this base model, let's say these are your base model weights right here, these are frozen. We're not going to touch them at all in this implementation here. Sorry, else I'm still under the weather. The weather change in New York, for anyone that lives here, it's crazy. I've just gotten sick completely randomly out of nowhere, but sorry for the random spiel here. But here with this base model weights, right, we're going to freeze them. We don't want to mess with them. What QLoRA does is it adds these smaller adapter weights and injects them into certain points of the model. Think of them almost as kind of like sticky notes, basically. And these are the ones that we're going to be training on. And these are much, much smaller. And we're just adding these basically to those base model weights, basically, in certain places, essentially. So with the idea of this, rather than kind of fine-tuning each and every single one of the base model's parameters, keep that frozen, introduce these kind of adapter matrices here, essentially, and train upon these and merge these with the base model. So you can think of, right, the final form of this, right, is you have your base model, and then you can kind of merge the different adapters that you've trained. Since these are much smaller, let's think of, for example, language translation as a use case. Obviously, a lot of LLMs are now multilingual, So this is just an example, but let's say, for example, it's not specialized across all languages. Maybe you have a Spanish adapter that you trained on. Maybe you have a French adapter that you trained on. Horrible writing as always, I'm sorry. And then maybe something like Portuguese or whatever it is that's happening right here, right? So with these different adapters, basically, they have specialized kind of smaller components that you're infusing into that base model. And there's two ways you can go about it. You can either, one, merge into the base model, and then you run inference simply by invoking that base model itself. So this is post-training, obviously. Or two, you could also do multi-adapter inference. So rather than merging them, and this is what we've talked about in previous videos, you can kind of invoke your target adapter, which is laying separate from this base model. So the base model is still associated with it, but then you have your target adapters like A1, A2, A3, wherever else it is, you might, however many adapters you might have, right? So that's the concept where you have the base model and you have these standalone adapters that you can invoke separately, or you can also merge them as we were talking about. So this allows for, right, if you think about the different use cases, when you have things such as personalization, so let's say you have specific users with specific order histories or something of that sort, and you want to customize based off their data and their experiences in terms of like the experience you provide for them. Hyper-personalization is where I often see kind of adapter use cases, and then very domain-specific kind of use cases, right? So if you have something very specific within healthcare, for example, you have data that is very kind of specialized for certain purposes and that you want to invoke each and every single one of them, kind of around that part. Those are the different types of use cases you can think. The one I've personally seen at least a lot with is hyper-personalization in the field. But you essentially want to ensure, right, not just the use case, but I always emphasize this, any ML model is only as good as the data that it has access to or that it's been trained on. So if you don't have the requisite data to conduct fine-tuning or training, then you want to make sure, right, like you might not actually get any value even if you are able to train it. It needs to be quality data that fits for the use case that you are trying to train it on. So if you have users, different users with custom data and things of that sort, if there's not enough custom data to kind of identify each user, you're not going to see many benefits, right? So that's where you kind of want to evaluate what is the data that I have, what is the quality of the data I have, and does it map over to a use case that actually makes sense to implement kind of this type of fine tuning on. And you can also check out the video, I'll link it down below, of when to use like fine tuning versus agents versus like kind of like RAG. It's not always just one or the other. There's many different ways you can utilize all these, but a lot of it is dependent on the data you have available to kind of make that informed decision in terms of what's the right way to go forward. So I'll link that down below as well, but just keep that in mind that even though this is like a neat technique, it will only work if you have the requisite data there that will make sense. So with that being said, I think the second thing, I had to scroll up, I completely forgot what I was going to say, is how can we implement this with Hugging Face? So we've talked so much about why Hugging Face is so valuable for us in this process, right? And how we could use it. And a lot of that is due to some of the different libraries it provides. And we've talked about in previous videos, right? I encourage you to check out the ones earlier in this playlist about how it provides the transformers class that lets us interface with the models. And then on top of it, there's all these kind of subclasses such as trainer, which lets you simplify transformer model training. And then also another one specific for today is TRL, Transformers Reinforcement Learning. And what this does is it exposes different types of training and simplifies how you can kind of do this. So like we said, right, if you just use low-level PyTorch code, you can still do that, but it's still pretty annoying to kind of set up the algorithm, set up your architecture and everything of that sort. The whole point of transformers and Hugging Face is it kind of simplifies the process while keeping it in a singular ecosystem for you. So what it does is it provides different trainers, similar to that base trainer that we saw. There's an SFT trainer, there's a GRPO trainer, and more basically. So different training algorithms are kind of provided for you with kind of pre-configured structures that are expected for that training, and simplification over a lot of maybe the grunt work you might have to do with things like tokenization or things of that sort, to basically kind of make it simple for the end user to just say, here's my data, this is the exact training algorithm I want to use, pick the appropriate kind of subclass or subtrainer here, and then fit it in the constructs that have been defined there. So you can think of these as like really like wrappers that are continuing to build on that transformers library, which also builds on, right, that lower level torch code that can get pretty intensive and kind of extensive in terms of what you're working with. So for our use case, we're going to use the SFT Trainer, which is once again that managed module that's provided for us, and we'll implement PEFT through it. And even PEFT, right, is another pre-configured library provided by HuggingFace. So within PEFT, there will be a number of different parameters that you can kind of configure, basically, such as rank, like basically parameters around the actual kind of data science setup itself. Like I said, I'll link the documentation for what each of these parameters means, but you can play with it, and even if it doesn't make full sense, just you can also see that there's kind of pre-configured kind of setups for different types of models from what people have vetted. That's basically what I did. I don't fully understand the matrix algebra and everything behind it because I'm not full out in the data science world, but you should try to read through all those parameters just like I did here, just to get a better understanding in terms of what exactly is happening here and what are we going to tune. So what PEFT does is, like I was saying, is through that library, you can basically set up a LoRa config, which basically adjusts these different parameters, such as the R value, the alpha value, and things of that sort. And we'll see all of these implemented in that LoRa config. So TRL is library number 1, and then exposes SFT Trainer. PEFT is library number 2, which allows for us to define our QLoRA config, basically. And then that PEFT config, you can feed into that SFT Trainer class, which is provided basically by the TRL library. So that's where Hugging Face kind of simplifies matters for us, basically. Whereas this would be a lot of manual setup, right, if you're doing this by yourself, essentially. And then what we'll do is, right, now we'll get hands-on for our sample today. I just wanted to take a Llama 3 8B model, just a smaller model here, and then basically take this, and I made a bunch of mock artificial data, which is not the best, with random kind of generic questions of myself. And then we're going to fine-tune this using those constructs from Hugging Face transformers, basically implementing QLoRA, and then we'll see our generated adapter weights, and we'll see how our model with the adapter weights merged performs compared to the base model standalone, right? And then obviously evaluation, there's a lot of nuances within that. Here we'll more kind of eyeball it just because it's a very simple use case, but there's also a whole evaluation flow that we'll talk about and slowly introduce as we get into this. So with that being said, let me hop into, sorry for all the sniffling, I'm sure it's very annoying to hear. Let's hop right into the actual notebook instance itself. And what we'll do is here in SageMaker AI, I've created a G516XL classic notebook instance. We're going to be doing the fine-tuning directly in the notebook itself. Like I said, for scaling up, and this is also earlier in the playlist, sorry, don't want to keep referring to that, but you would probably want to use something like a SageMaker training job to have a more production-ready workflow. Here, I just want to introduce PEFT for you. So it's very simple end-to-end in a notebook that you can kind of execute, but in a production grade setting, you will want to fit it into a SageMaker training job, and we'll probably have another video and sample around that in terms of how you can do it. But take a look at the SageMaker training job video in terms of interfacing with Hugging Face models. It'll be very simple to kind of take the same code and inject that within that container as well, right? So to scale up, I would use a SageMaker training job, and in future videos, you might be getting this question. When you have larger models that don't necessarily fit, even when quantized into a single GPU's memory, we're going to have to look at different forms of distributed kind of data parallel in terms of how can we shard the model while retaining like the performance there, and that's where we'll introduce things like PyTorch FSDP, Hugging Face Accelerate, where we're going to need multiple instances, right? So for this example, at least one GPU will do, even though if it is a beefier one, we probably don't need this big of a one. You can probably bring it down a little because Llama 3 8B is a smaller model. But what we'll do is in this sample, let's hop right into the notebook, and I'll link the code as always down below. In the sample, we'll talk through those exact constructs we've used before, install them, and basically work with fine-tuning Llama. So to get started, right, some of the prerequisites, make sure you have a Hugging Face access token because you need that to be able to get access to that Llama 3.1 model. And for the Llama 3.1 model, you're also going to have to request access, by the way. So I was granted this right here, basically, but you need to request access and get permission. Should be pretty simple or standard there once you request that. And what we'll do is for our setup, we'll install the different libraries I was talking about. So transformers, as always, is how the way we will interface with these models. PEFT will let us kind of define our QLoRA config. TRL will expose that SFT Trainer class, basically, for supervised fine-tuning, where we can kind of inject our QLoRA config. And then that will essentially kind of set up our environment to be able to work with all this. So we come down here, you'll see in PEFT, we're going to import LoRa config, basically. This is once again defining QLoRA here. I don't know why I always put my Hugging Face token here, but this is yet another one I'm going to have to delete there. But you can set this token up here, you can enter this here, and proceed. And then what we're going to do is we're going to, in this cell, there's not much here. We're just going to basically make a dummy data set. So this is random facts about me that I added here essentially. And I'm going to just inject them into some dummy templates for us to feed in as our training data. Some of these won't make sense because I'm just randomly sampling these into different things. So for input, for example, what is the user's job and domain? It says I'm a boxer. That doesn't make much sense, as much as I'd love for that to be true. But in general, the model will get a general knowledge, right, in terms of my hobbies, my profession, and things of that sort. And the hope is with that extra knowledge, it'll be able to give at least slightly more customized answers when I ask questions about myself, whereas the base Llama 3.8b model, right, might not necessarily be able to do that. So if we come here, you can see what an example kind of input looks like in terms of what we're working with, and you'll see what kind of projects do we work on usually. Once again, the input is not necessarily accurate because it's random sampling here, but it's saying the user is training for an amateur boxing fight while working full-time as an engineer. And if we go down, I'm going to convert this to the HuggingFace datasets format. If we remember, datasets is kind of the standard format for HuggingFace data in terms of how all of this will work. We also did some prompt engineering to structure this basically into like a singular string for that text input, where we have both the instruction and response. You can kind of format this as you need in terms of what you're working with. But this data will split into a train and test here. And then all the rest of this, the initial setup at least, is very, very similar to what we saw with the default trainer class, even with the smaller BERT model. So we're going to pull down the tokenizer for Llama 3.8b. And once again, neatly just using transformers here, we can pass in that model ID right there. We pull those artifacts down. And then, right, the Q part of QLoRA is quantize. So quantization is a form of model compression, basically. In this case, we do 4-bit quantization, sorry. And this is essentially going to reduce the memory footprint of the model, right? Another reason QLoRA is so effective is, especially for inference, we're going to be quantizing the model. Obviously, there's a little bit of data science accuracy that's lost while doing that, but it is negligible in most use cases, but you want to evaluate that. We're going to quantize the base model itself. So even though those weights are untouched, we still want to optimize for the memory footprint that our inference is going to be taking, right? So the quantization of this model is that Q part of QLoRA, where the base model itself gets quantized there. And then we're going to load this model in 4-bit quantization, as we said. So we're going to pass in that model ID right there, and we're going to prepare it. So these loaded model artifacts that we're pulling down, we're going to prepare using that bits and bytes kind of config, basically, for 4-bit quantization. Once again, this is another benefit of QLoRA and why it's so popular, because the base model is also getting a reduced memory footprint, basically. And then we can set up our actual LoRa config. This is once again from the PEFT library, and you can see all the different kind of parameters here that you can enable, which are more data science specific. And you can see this, I've linked it in the kind of documentation here as well. But this is all very, very specific to kind of the adapter matrices itself and how you want to tune them. So you can basically take a look and try to understand better in terms of what each of these say. I have a higher level understanding, but you don't need, just like that, you can also kind of have a higher level understanding like I do here. But if you're very interested in the data science, right, I'll link the paper down below too in terms of how the actual linear algebra is happening here and the kind of matrix operations that are essentially happening. For those of you that are like not too familiar with deep learning, a lot of it is just linear algebra and then probability for the most part in terms of what's happening in the math. I know I simplified that like crazy there, probably get some hate from some data scientists there, but you can get a better understanding by reading through the research papers. Even if you don't have that understanding or want that understanding, I would still read it to get a understanding. That's at least what I did of what exactly is happening here, right? So you can configure these depending on your use case. And like I said, there's a lot of predefined ones for different models that you can take a look at. I just grabbed this for Llama as a predefined one from what I saw in the HuggingFace docs. And now once that's configured, right, from the TRL library, we can set up our supervised fine-tuning kind of like trainer class right here. So first for the config, this is very similar to the training arguments, right, that we had for the base trainer class. And we'll see that we pass an output directory, which is where we want our model artifacts saved, this QLoRA PEFT output right here. And we can pass in different parameters. I'm just going to do a singular epoch here, but you can tune all of these as you want. Save strategy epoch, just to make this all clear here. And then if you notice a few SFT specific parameters here, I'm going to say the dataset text field is text. So we want to parse what's in that key basically, which is our prompt that we kind of configured there. And we set that up here. And then this SFT trainer, very similar to how we pass in the trainer, right? We can pass in our model, we can pass in the SFT config here essentially. And you can see the different parameters here in the kind of docs here if you want to adjust anything. And then we also very importantly pass in our PEFT config to our SFT trainer. So what we've defined here as our LoRa config, that's all we're passing in for our SFT trainer class to basically kind of get injected in with, right? And then a lot of things are taken care of. So tokenization, we don't need to provide a tokenizer like we did with the base trainer class. It's automatically picked up on by the base model itself and things of that sort. And then we can pass this in here, right? And essentially then we have our final trainer class kind of built out, and then we can conduct training. So here it's just a single epoch that happens, but once this training happens, this shouldn't take more than a few minutes on this instance type. Like I said, a G516XL might be a little overkill here. You can get kind of the final metrics in terms of loss and anything else that you're dealing with. Now we want our model weights, right? Because this train model by itself is not going to be much value in a production grade setting. What we're going to do is we're going to save these adapter weights to that adapter directory right here. So this QLoRA PEFT output, I'm going to make an adapter key right here, and you'll see that there's these serialized model artifacts post-training. So this will be much, much smaller basically than the base model itself. But these weights right now are standalone, right? What we want to see is if we merge these adapter weights into our base model, how much better will our base model basically perform, in this case, about questions about myself, right? Or about the user specifically. So what I wanted to do is, before I even merge it, let's just see how the base model does with some sample prompts. I'm going to say what types of projects I usually work on, where do I live at, what city am I in, what sports or hobbies, basically things of that sort, right? And just ask these questions. I'm going to pull down those model weights again. I probably shouldn't have done that there because we already loaded it up earlier. But here I'm going to pull it down, and then we can see that here it's very generic answers that are kind of being given. I live in the city of blank, in the state of blank. And then here it just says I'm a software engineer. I've been working in the field for 10 years. Favorite programming language is Python. Very generic answers that it's just outputting because it doesn't have any custom knowledge about myself, right? Now let's see with our kind of fine-tuned adapter, if we merge it to the base model, can we see a difference in terms of these outputs? So I'm going to specify my base ID again, and I'm going to specify my adapter directory, which contains my adapter weights basically. And then I'm going to make a directory called merged model right here, which should have both my base model weights and artifacts and my adapter weights basically and stuff, right? So what I'm going to do here is then pull that tokenizer again, load the base model once again. And what I'm going to do is right here, specify my PEFT model, which is the base model is Llama 3, and then my adapter directory is the one that contains these artifacts and resources, right? So that's essentially what I'm going to be doing here. And then what I'll do then is, this is the key API call here. Model.merge and unload is what we're going to be using here, where we kind of merge this LoRa adapter into the base model weights essentially. So once I do that, I'm going to save that into this merge directory, which will reflect upon that. This is containing both my adapter weights and my base model weights basically. So once we merge this, I'll define the same function once again in terms of what's happening, just going to run inference on those exact same prompts. And if you see here, the answers aren't the greatest because once again, our data was just randomly sampled without the right types of answers, but we'll see some of the customized answers make more sense. So we talks about fitness, boxing, basketball, which is things that I like. The user lives in a big US city with many tall buildings. I guess that's one way to describe New York. And then here you can see boxing is brought up again. And then specifically, it realizes that I'm a senior ML engineer at AWS or a large cloud company. So we can see just purely through kind of learning of some very kind of crappy data, we're able to introduce some more customization here, specialized for myself. Now you can imagine if you scale this up with actual quality data across hundreds of different users that you might be working with or things of that sort, then you can imagine this is really, really going to get very, very powerful here because like you can hyper personalize and hyper scale across many different users. But yeah, that at a high level is mainly what I wanted to introduce today. This is a very, very powerful technique that you can use to really kind of personalize your generative AI applications. Like I said, there's a use case for using fine-tuning with techniques such as this versus also using agents and kind of like RAG or anything of that sort. And it doesn't have to be one or the other. You can use many of these in conjunction. A lot of it depends on your familiarity and your experience and our team's experience too. Like I said a lot of times in this video, I'm an ML engineer. I'm more so on the infrastructure side. This data science stuff is still, like I have an understanding, but I don't have a deeper understanding of it. So if you have data scientists, for example, on your team that really, really understand the nuances behind this research and things of that sort and know how to fine-tune this for max performance, that can also have an impact on the type of choice that you want to take. But I'd say the biggest delimiter in terms of determining what method to go with is understanding kind of the actual data that you have. Because even for myself as an ML engineer, just from reading more and learning, any of you can do this, right? If you have just a general understanding, of engineering and things of that sort. Just from reading and understanding more about PEFT or QLoRA, I was able to implement it pretty simply. Obviously not at scale, this was more of a POC, but just think of the data that you have accessible for you. And then a lot of these techniques, due to so many higher level frameworks and libraries being available from places like HuggingFace, right, will make it pretty simple for you to implement, even if you're not like masters or PhD in data science or anything of that sort. But yeah, didn't mean to ramble on too much more there. If you have any questions, please leave them down below in the comments, as always, or LinkedIn or Twitter, wherever it is comfortable. Feel free to reach out to me. If you enjoyed the video, feel free to leave a like and subscribe. And I'll be back with a lot more in this space. I think the next video in this, I'll showcase how you can implement this on a SageMaker training job, and then maybe operationalize this in a MLOps workflow that will deploy to a SageMaker endpoint, right? That has multiple adapters maybe that you can kind of invoke using the multi-adapter inference feature. So we'll try to take this from proof of concept to more of a production grade setting. So stay tuned for more there. Like I said, there's a lot more within the HuggingFace ecosystem itself that is very important for ML engineers, I think, to be aware of. So I'll do my best to kind of bridge that gap for you guys, or showcase what I'm learning in the process. But yeah, thank you everyone for watching, and I'll be back soon.